Welcome student. In the lecture series of heat transfer, in the first two parts, we studied the fundamental things of the subject like thermal conductivity, modes of heat transfer, laws governing different modes of heat transfer and different heat conduction equations in Cartesian, cylindrical and spherical coordinate system. Now we will start next chapter entitled Conduction Heat Transfer. Under the part 1 of this lecture, the content covered follows like thermal resistance, boundary conditions, heat conduction through plane wall and heat conduction through composite wall, an example based on the above theory. So let's start with our first topic, thermal resistance. Here our objective behind to learn thermal resistance is to show how thermal circuits may be used to model heat flow, much as electrical circuits are used for current flow. We are very familiar with Ohm's law and so often use it as analogy when doing calculations involving heat transfer problem analysis. Thermal resistance. When two physical systems are described by similar equations and have similar boundary conditions, these are said to analogous. The heat transfer processes may be compared by analogy with the flow of electricity in an electric resistance. As the flow of electric current in the electrical resistance is directly proportional to the potential difference dV, similarly heat flow rate is directly proportional to temperature difference dT, the driving force for heat conduction through a medium. As per the Ohm's law, we have current I is equal to potential difference dV by electric resistance R, say equation number 1. By analogy, the heat flow equation from Fourier's law we may be written as heat flow rate Q is equal to temperature difference dT by dx by K, say equation number 2. By comparing the equation 1 and 2, we find that I is the analogous to Q and dV is analogous to dt and R is analogous to the quantity dx by K. The quantity dx by K is called thermal conductance resistance RTH conductance. The reciprocal of the thermal resistance is called thermal conductance. It may be noted that the rules for combining electrical resistance in series and parallel apply equally well to thermal resistance. The concept of thermal resistance is quite helpful while making calculations for flow of heat. Now it's time to learn about another term, boundary condition. Both topic, thermal resistance and boundary condition, or you can say initial condition, is helpful to understand the different theories and problems related to this chapter. Boundary condition. The heat conduction equation we derived in our previous lecture using an energy balance on a different element inside the medium in different coordinate system, and they remain the same in any case of thermal conditions on the surfaces of the medium. That is, the differential equation do not integrate any information related to the conditions on the surfaces such as the surface temperature or a specified heat flux. And the heat flux and the temperature distribution in a medium depends on the conditions at the surfaces, and description of a heat transfer problem in a medium is not complete without a full description of the thermal conditions at the bounding surfaces of the medium. So, the mathematical expression of the thermal conditions at the boundaries are called boundary conditions. Let a differential equation d square T by dx square is equal to 0. For getting solution of this equation, we should removing derivatives or integrating the equation 2 times, and thus the solution of differential equation involves two arbitrary constant. Here C1 and C2 are the arbitrary constant. It follows that to obtain a unique solution, we need to specify some conditions to that, forcing the solution to satisfy these conditions at specified points will result in unique values for arbitrary constant and thus a unique solution. But since the differential equation has no place for additional information or condition, we need to supply them separately in the form of boundary or initial conditions. Consider the variation of temperature along the wall of the brick house in a winter. The temperature at any point in the wall depends on the conditions at the two surfaces of the wall, such as the air temperature of the house, the velocity and the direction of winds, and the solar energy incident on the outer surface. The figure shows the different specific solutions for different conditions in house. The only solution that specify the condition, say boundary condition, that temperature T is equal to 15 degree centigrade at x is equal to 0 distance and the T is equal to 50 degree centigrade when x is equal to L. To describe a heat transfer problem completely, two boundary conditions must be given for each direction of the coordinate system along which heat transfer is significant. Therefore, we need to specify two boundary conditions for one-dimensional problems, four boundary conditions for two-dimensional problems, and six boundary conditions for three-dimensional problems. Boundary conditions must commonly encountered in practice are the specified temperature, specified heat flux, convection, and radiation boundary conditions. In this chapter, we considered that the heat is transferred by diffusion under one-dimensional steady-state conditions. As I already discussed in previous lecture that the term one-dimensional refers that only one coordinate is required to describe the spatial variation of different variables. Therefore, in a one-dimensional system, temperature gradients exist along only a single coordinate direction and heat is transferred completely in that direction. The system is characterized by steady state conditions if the temperature at each point is independent of time. Although their intrinsic simplicity, one-dimensional steady-state models may be used to accurately represent numerous engineering systems. Now move towards the main topic of our lecture, that is heat conduction equation for plane and composite wall, in which we will learn first case, assume uniform thermal conductivity. Consider a plane wall of homogeneous material through which heat is flowing only in x direction as shown in figure. Let L is the thickness of the plane wall, A cross-sectional area of the wall, K is thermal conductivity of the wall material, and T1, T2 temperatures maintained at the two faces 1 and 2 of wall respectively. The general heat conduction equation in Cartesian coordinate system is del square T by del x square plus del square T by del y square plus del square T by del z square is equal to 1 upon alpha del T by del tau. Equation number 1 that already proved in our last lecture. If the heat conduction take place under the conditions steady state, del T by del tau is equal to 0. One dimensional, so del square T by del y square and del square T by del z square is equal to 0. And with no internal heat generation, Qg by K is equal to 0. Then above equation is reduced to del square T by del x square is equal to 0, or you can say that d square T by dx square is equal to 0, equation number 2. By integrating the above equation twice, we have dt by dx is equal to C1 and T is equal to C1x plus C2. Say equation number 3, where C1 and C2 are the arbitrary constant. The values of this constant may be calculated from the known boundary conditions as follows: at x is equal to 0, t is equal to t1 and x is equal to L, t is equal to t2. Substituting the values in equation number 3, we get t1 is equal to 0 plus c2 and t2 is equal to C1 into L plus C2. After simplification, we have C2 is equal to T1 and C1 is equal to T2 minus T1 divided by L. Thus equation 3 reduces to T is equal to T2 minus T1 divided by L into X plus T1, say equation number 4. The equation 4 indicates that the temperature distribution across the wall is linear and is independent of thermal conductivity. Now heat through the plane wall can be found by using Fourier's equation as follows. Q is equal to minus Ka dt by dx, the Fourier equation where dt by dx is equal to temperature gradient. But dt by dx where T is equal to T2 minus T1 by L into X plus T1. By simplification we get the equation T2 minus T1 divided by L. So Q is equal to minus Ka T2 minus T1 divided by L, and that is equal to Ka T1 minus T2 divided by L, say equation number 5. From equation number 5 we can be written Q is equal to T1 minus T2 divided by L by Ka, where L by Ka is thermal resistance to heat conduction. Let the thermal conductivity vary with temperature according to direction. So case 2 of variable thermal conductivity. As shown in figure, a plane wall having a length L, heat transfer of the plane wall in which the conductivity is considered is equal to K0 into 1 plus beta T, where K0 is the thermal conductivity at 0 degree centigrade and beta is temperature coefficient in 1 upon degree centigrade. The value of beta is positive for non-metals and insulators. The beta is negative for metallic conductors, and beta is equal to 0 means uniform thermal conductivity. Now let's learn about heat conduction through composite wall. Consider the transmission of heat through a composite wall consisting of a number of slabs. The electrical analogy of thermal circuits is shown in figure. Let LA, LB, LC is equal to thicknesses of slab A, B and C respectively, also called the path length. Ka, Kb and Kc are the thermal conductivities of the A, B and C slab respectively. Also the T1 and T4. Here T1 is greater than T4, the temperature at the wall surfaces 1 and 4 respectively, and T2 and T3 are the temperature at interfaces 2 and 3 respectively. Assuming that there is a perfect contact between the layers and no temperature drop occurs across in the interface between the materials. Since the quantity of heat transmitted per unit time through each slab or layer is same, then we have from the Fourier's law Q is equal to Ka into A T1 minus T2 divided by LA is equal to Kb into A T2 minus T3 divided by LB and is equal to Kc into A T3 minus T4 divided by LC, say equation number 1. Rearranging the above expression, we get T1 minus T2 is equal to Q into LA divided by Ka into A. T2 minus T3 is equal to Q into LB divided by Kb into A, and T3 minus T4 is equal to Q into LC divided by Kc into A. Adding these equations, we get Q is equal to T1 minus T4 divided by LA by Ka into A plus LB divided by Kb into A plus LC divided by Kc into A. Here LA divided by Ka into A is the thermal resistance of slab A, LB divided by Kb into A is the thermal resistance of slab B, and Lc divided by Kc into A is thermal resistance of slab C. If the composite wall consists of n slabs per layer, then the term is, in general format, Q is equal to T1 minus Tn plus 1 divided by sigma 1 to n L divided by Ka, where n is equal to number of slab or layer. Also in general form, we can write the equation Q is equal to delta T overall divided by sigma RTH, where RTH is the thermal resistance of all slab. If composite wall is connected in series and parallel, then electric analog is shown in figure. Here as per the Fourier's law, Q is equal to T1 minus T2 divided by RTH total, where RTH total is thermal resistance. RTH total can calculate from the equation is equal to RTH A plus RTH equivalent plus RTH D. Here RTH A is the thermal resistance of slab A, RTH equivalent is thermal resistance of slab B and C, and RTH D is the thermal resistance of slab D. The equivalent resistance RTH equivalent can be calculated by the equation RTHB into RTHC divided by RTHB plus RTHC. Here the Ka, Kb, Kc and Kd are the thermal conductivity of slab A, B, C and D respectively. Now, in heat conduction through composite plane wall, considering the thermal contact resistance means the temperature drop at interface in composite wall. Let me explain in detail. The thermal contact resistance. In a composite or multi-layer wall, the calculation of heat flow are made on the assumptions. Number 1, the contact between the adjacent layer is perfect, and number 2, at the interface there is no fall of temperature. Number 3, at the interface the temperature is continuous, although there is discontinuity in temperature gradient. In real systems, however, due to surface roughnesses and void spaces usually filled with air, the contact surfaces touch only at discrete locations. Thus, there is not a single phase of contact, which means that the area available for the flow of heat at interface will be small compared to geometric phase area. Due to this reduced area, the presence of air voids, a large resistance to heat flow at interface occurs. This resistance is known as thermal resistance, or you can say that thermal contact resistance, and it causes temperature drop between two materials at interface as shown in figure. The figure shows the composite wall of layer A, B and C, in which the temperature drop at the interface between layer A and B and interface between the layer B and C. The contact resistance are given by RTH conduction is equal to T2 minus T3 divided by Q by A, and RTH BC conduction is equal to T4 minus T5 divided by QA. Also the figure A and B shows ideal or perfect thermal contact and the actual imperfect thermal contact. In first figure, we shows between the layer 1 and 2 no temperature drop at interface, and in second figure the temperature drop delta T is there. In composite wall, the fluid layer is considered both side or single side. While dealing with the problem analysis of fluid to fluid heat transfer across a metal boundary, it is useful to adopt an overall heat transfer coefficient. As shown in figure, there is a plane wall having a length L and thermal conductivity K. The temperature T1 and T2 are the temperature of the plane wall surfaces. Here the THF and the TCF are the temperature of hot fluid and cold fluid from the both side of metal wall. The thermal resistance is 1 upon HF into A of hot film, and the thermal resistance 1 upon HCF into A is for the cold film. Here HF and CF is for the hot fluid and cold fluid. According to the Newton's law of cooling, the heat transfer by convection Q is equal to HHF into A into THF minus T1, and the heat transfer by convection in cold film side is Q is equal to HCF into A into T2 minus TCF. Inside the plane wall, the heat transfer through conduction, and that is calculated by the Fourier's law. Q is equal to K into T1 minus T2 divided by L. So now by rearranging, we get THF minus T1 is equal to Q divided by HHF into A. T1 minus T2 is equal to Q into L divided by Ka, and T2 minus TCF is equal to Q divided by KCF into A. So THF minus TCF, adding these all equations, we get Q into bracket 1 upon HHF into A plus L by Ka plus 1 upon HCF into A. If U is overall coefficient of heat transfer, then Q is equal to UA THF minus TCF, and that is equal to A into THF minus TCF divided by 1 upon HHF plus L by K plus 1 upon HCF, where U is equal to 1 upon HHF plus L by K plus 1 upon HCF. Let's learn the example based on these theories. So number 1, an exterior wall of a house may be approximated by a 0.1 meter layer of common brick having a conductivity K is equal to 0.7 watt per meter degree centigrade, followed by a 0.04 meter layer of gypsum plaster having a thermal conductivity K is equal to 0.48 watt per meter degree centigrade. Then what thickness of loosely packed rock wool insulation having thermal conductivity is 0.065 watt per meter degree centigrade should be added to reduce the heat loss or gain through the wall by 80%. As shown in figure, here common brick having a thickness La is equal to 0.01 meter, Lb is equal to 0.04 meter, and Lc we want to calculate X in meter. The thermal conductivities of common brick say Ka, gypsum plaster say Kb, followed by the rock wool say Kc. Consider two cases to solve this example. So case 1, rock wool insulation not used. Then according to the Fourier's law, Q1 is equal to A area into delta T divided by thermal resistance L by Ka plus L by Kb. Putting the value in this equation, A into delta T divided by 0.1 by 0.7 plus 0.04 divided by 0.48. Consider case 2 when rock wool insulation used. Then Q2 is equal to A into delta T divided by La by Ka plus Lb by Kb plus Lc by Kc. Putting the value in this equation, we get A. In case 2, consider rock wool insulation is used, and then equation is Q2 is equal to A into delta T divided by La by Ka plus Lb by Kb plus Lc by Kc. Putting the values in this equation, so A into delta T divided by 0.1 divided by 0.7 plus 0.04 by 0.48 plus X divided by 0.065. But Q2 is equal to 1 minus 0.8 Q1, and that is equal to 0.2 Q1, which is given in the data. So from these two cases, we solve this example. A into delta T divided by 0.1 by 0.7 plus 0.04 divided by 0.48 plus X divided by 0.065 is equal to 0.2 into A delta T by 0.1 divided by 0.7 plus 0.04 divided by 0.48. By simplification, we get the answer of the value of x, and that is equal to 0.0588 meter or 58.8 mm. The thickness of rock wool insulation would be 58.8 mm. The second example of the composite wall, in which we discuss about find the heat flow rate through composite wall, as shown in figure. Assume one dimensional flow, and here the conductivity of slab A is 150 watt per meter degree centigrade. Conductivity of slab B, Kb, is equal to 30 watt per meter degree centigrade. Kc, conductivity of slab C, is 65 watt per meter degree centigrade, and conductivity Kd of slab D is 50 watt per meter degree centigrade. So here let us solve the example, and the thickness of slab A is 0.03 meter, slab B and C having a length of 0.08 meter, and slab D having a length of 0.05 meter. The areas of the particular slab for A is 0.1 into 1, that is 0.01 meter square. For slab C is 0.007 meter square. For B 0.003 meter square, and for D 0.01 meter square. It is a thermal circuit diagram from electrical analogy. Here the resistance of slab A is RTH-A, the resistance of slab B is RTH-B, resistance of slab C is RTH-C. Here resistance B and C are in parallel, and then the resistance of slab C is RTH-D as is in series. Now heat flow rate Q, thermal resistance are given by the RTHA is equal to L by K, and putting the values in this equation. So we get the RTHA, the thermal resistance of slab A is 0.02, the thermal resistance of slab B, that is equal to RTHB, is equal to LB by KB into AB. Putting the value in this equation, we get this resistance of slab B is 0.89, the resistance of the slab C is equal to LC by KC into SE, and we get the value 0.176, and the thermal resistance of slab D, that is equal to LD by KD into AD, and we get thermal resistance of that slab D is 0.1. The equivalent thermal resistance for the parallel thermal resistance RTHB and RTHC is given by 1 upon RTH equivalent is equal to 1 upon RTHB plus 1 upon RTHC. So that is equal to 1 upon 0.89 plus 1 upon 0.176, and is equal to 6.805. So RTH equivalent is equal to 1 upon 6.805 and is equal to 0.146. Now the total thermal resistance RTH total is equal to RTHA plus RTH equivalent plus RTHD, and is equal to 0.267. Finally, the equation Q is equal to delta T total divided by RTH total, and is equal to 400 minus 60 divided by 0.267. We get the answer 1273 per 4 watt. Take the next example of a mild steel tank having a thickness of 12 mm, contains water at 95 degree centigrade. The thermal conductivity of mild steel is 50 watt per meter degree centigrade, and heat transfer coefficient for inside and outside the tank are 2850 and 10 watt per meter degree centigrade respectively. If the atmospheric temperature is 15 degree centigrade, then calculate the rate of heat loss per meter square of the tank surface area and the temperature of the outside surface of the tank. As per the given data, as shown in figure, there is a slab having a thickness of 12 mm and the hot fluid temperature is 95 degree centigrade and the temperature of cold side is 15 degree centigrade. T1 and T2 are the temperature of surface temperature of the tank wall. As per the given data, the thickness convert into the meter and is equal to 0.012 meter. Conductivity is 50 watt per meter degree centigrade. So first, rate of heat loss per meter square of the tank surface area, and that is Q, is equal to UA THF minus TCF, where HF and CF represent the hot fluid and cold fluid. The overall heat transfer coefficient you found from the relation 1 upon U is equal to 1 upon H of hot fluid plus L by K plus 1 upon H of cold fluid. So is equal to 1 upon 2850 plus 0.012 divided by 50 plus 1 by 10. So we get the overall heat transfer coefficient is 9.94 watt per meter square degree centigrade. So finally we get the value of Q, that is 795.2 watt per meter square. Our second answer, the temperature of the outside surface temperature of tank T2, we get from the equation Q is equal to HCF into 1 into T2 minus TCF. So Q is equal to 795.2 is equal to 10 into bracket T2 minus 15. So we get the answer of T2, and that is equal to 94.52 degrees centigrade. One can use the following reference books for the subject heat transfer, and in which heat and mass transfer by P. K. Nag, heat and mass transfer fundamental and application by Yunus Angel, heat and mass transfer by Mills and Ganeshan, fundamental of heat and mass transfer by Incropera and David, heat transfer by J. P. Holman, and heat transfer by R. K. Rajput. Thank you for watching, keep learning, and good luck to all. In next part of this chapter, we will discuss about the heat transfer by conduction through cylindrical and spherical wall.